tau is equal to 2 pi, but as pure mathematical constants, is one better than the other? Pi is the ratio between the circumference of a circle and its diameter. Half the circumference is equal to pi r, making the full circumference equal to 2 pi r. Since tau is 2 pi, we can also say that the circumference is equal to tau times r. Tau is the ratio between the circumference of a circle and its radius. Another point in favor of tau is its intuitiveness of radian measures. A quarter of a turn is tau over 4 radians, half a turn is tau over 2 radians, so on and so forth until a full turn is exactly tau radians. This means that our sinusoids are affected as well. The period of standard sine and cosine functions become tau instead of 2 pi. This actually makes it easier to pick out the period from a sine function. Take this one for example. Sine of tau over 4x. We know that it goes 1 full cycle every 4 units of x, making its period 4. Whereas if I were to try to get the period of sine of pi over 2x, an equivalent function, it's slightly harder. Now there are clear benefits of tau which have been stated several times before, but the ops always have something to say. Now some of their points make sense, like how it's easier to measure a diameter than it is to measure a radius. And they also have the benefit of the status quo. We're already using pi, it's not worth it to change to tau. But the main thing I would like to contend is their interpretation of the formula of the area of a circle. The standard formula for the area of a circle is pi r squared. In terms of tau though, it becomes tau over 2 r squared. And the ops claim that this is where the elegance of tau falls short, but is that really the case? I think the best way to introduce this defense is to first derive the formula. We first begin by splitting a circle into infinitely many triangles. 1, 2, 3, all the way to infinity. Right now, let's just go into LAD. We can deal with infinity later. In this arrangement, the length of this segment is tau r. Also, it's our circumference. The circumference is still here. More on that later. For now, let's look at one of these triangles. From our circle, we know that the legs of this isosceles triangle are equal to the radius, and since this is one triangle of n, the base has length tau r over n. Similarly, the vertex angle has measure tau over n. We have the legs, the vertex angle, and the base, and with this information we can derive the area of this triangle using the sine formula. The formula is 1/2 sine of theta times a times b. Now plugging in our values, we get 1/2 times the sine of tau over n times r squared. Notice how we aren't really using the base, and I actually want to point out that with this approach, the arrangement of our triangles does not matter. In fact, we could have kept the triangles in a circle as is, and this proof would still work. We're maintaining the integrity of our circumference. Now that we know the formula to get the area of one of n triangles, let's look at the big picture. We have n total triangles, meaning that the total area of our circle is going to be n times the area of 1. This is where I'm going to bring back infinity. We have an infinite number of triangles, so our total area becomes the limit of n times a of n as n approaches infinity. So, looking back at our formulas, the limit looks like this. Now, when I did this, I was at first kind of lost. As the number of triangles approaches infinity, the area of each approaches 0. But we're also multiplying this value that ever approaches 0 by a number that ever approaches infinity. So what does this equal? We can continue this with a substitution. So let u of n be equal to theta, or tau over n. We can rewrite this to be n is equal to tau over u of n. As n approaches infinity, u of n approaches 0. Now this allows us to rewrite our limit as so. Since multiplication is the same thing as dividing by the reciprocal, we can move this tau over u of n term under sine of u of n, and we get this. We can now move tau to the numerator, and oh my god, it's a special limit. To explain this, I think it's really nice to use a graph. The limit as sine of x over x approaches 0 is 1. Now, this applies when we substitute u of n for x. As n increases, u of n approaches 0. When u of n approaches 0, sine of u of n over u of n approaches 1. Therefore, back to our equation, this term cancels out to 1. and we are left with tau over 2 r squared. But so what? What is so special about tau over 2 r squared? Remember what I said about the circumference? The circumference is maintained in this formula. We can clearly see the relationship between the circumference of a circle and its area. On the other hand, the traditional pi r squared kind of sucks. We have pi, which is the proportion of the circumference to the diameter, but we are also multiplying by the radius. This just doesn't make sense, and to me, it's kind of disgusting. See ya.